All right. Cool. It is being shared. I'm gonna crack the door. All right. So y'all received a notification or a freaking what it was called, an announcement at some point that said, uh, "Hey, this is what we're going to cover." There's 5 questions or topics that he covered. I believe he said 4 questions is what's going to be in y'all's final, or do y'all know?
Yeah, right. Word on the street is 4.
But okay, well, you got 5 topics, so he's gonna take possibly 4 from that. If not, he'll take all 5. Who knows? Okay, so I'm gonna start in the order. So I'm gonna start doing natural frequencies. Um, I I have done previous material in natural frequencies. I have 3 reviews from each of the first tests from this semester, last semester, and 2 semesters ago. And then I did a final review a year ago that actually has these exact same topics from like, it's the same topics as that notification that he sent y'all. So a year ago, y'all can rewatch that. Pablo did one last semester for a final. Y'all can also watch that as well. Just have like a different perspective. I will be very honest. The rise back passivity criteria, we had the exact same question because there's literally not much material on that. So yeah, maybe, I mean, I'd go watch that, just see if Pablo explains it better than I do, or just, get a point of view. But I'm going to start off in doing the natural frequencies. So I'm going to read this question, and it's not exactly how it is. So, okay. So the zero state RLC network shown in figure 88 is operating in the time domain where network excitation is provided by the independent voltage source, e.g. of t. You're asked to do the following. Well, I'm not going to say that because we're not doing it. So essentially, this is a problem, I believe, that was like network responses. It was under that topics in a problem set that I found. It's not from y'all's problem set. It's from a different problem set. But essentially, this network response function problem is extremely similar to natural frequencies. There's only a slight tweak in the end. Can anybody kind of spoil it in terms of like what I'm going to do, or do y'all remember that far back, or like where we at? What's there's exactly, I agree. And the denominator, yep. But what do you'll eventually have this K, you'll eventually have this K in DS, right? Y'all agree with me on that? Okay. Well, how do you find your natural frequencies from a K in DS?
You look at the impedance of the.
Well, you'll have what do you call it?
If it's admittance, the open circuit is on the numerator, short circuit is on the denominator, and then if it's impedance, you flip it, and then stability is on the left hand.
Oh, I think you look if it's positive or negative, right?
I agree with what you said. I agree kind of what you're saying. What were you saying, Kyle? Yes. How do you do that? You just find the roots of the numerator and the denominator. So no. Well, yes, but it's a lot easier on your calculator. You literally can just say find the poly or complex polyroots. Thank you. Yes, and find them. So we're gonna go through this step by step. But yeah, that's just kind of the general. Can anybody point me in the direction of how we start? MAME. I agree. Is everything correct to let us perform MAME? No. What do we got to do? Cool. How do we do that? We have a capacitor in parallel with that current source. Yes. I agree. So that just becomes, I'm going to just draw this in. I'm not redrawing this entire circuit. All right. So like you said, we multiply it with its impedance. What is the impedance of that capacitor? 1 over SE3. I agree. So that then becomes GM over SC3 times V2 of T minus V4 of T. And we will get there eventually of what those things are. All right. I'm going to start this. What is in mesh 1? And give me the impedances. I'll give you those.
R1.
Yep, R1. Yep. Is that it? Cool, I agree. What's being shared? Negative 1 over SC3, and they're negative because they're being what? As I just said, yep. Same thing here. All right, so we'll start it off with this one. What's next? Which the impedance is. Yup. And then one more. Yup. All right. And then IM1, IM2. Oh, yeah, if you have any questions anytime, let me know. So, yeah. Making sense so far? Okay. What is the sources in mesh 1? Yup. I'm going to make it EG of S because, yep. You'd say negative? Oh, wait, I drew that arrow wrong. I'm sorry. I drew this arrow wrong. That is my bad. So negative or positive? Positive, I agree. Plus GM over SC3, V2 of S minus V4 of S. All right, cool. What's in mesh? I'm going to close these brackets, I guess. What is in mesh 2? I agree. And is there anything else?
Negative.
Yep. Yeah, you don't have to say it again, but negative that. If it makes sense, it makes sense. Negative that. Oh, sorry. Yep. Negative mu V1. Like I said, if you got any questions of what I've written down or whatever, literally let me know. I will not take offense to it. Okay. What would you say we do next?
Find what V2 of S and V4 of S is.
I agree with that. And we got one more that we need to find.
V1 of S.
Yep. Okay. So we're going to start V1. V1 of S. It is the voltage across that resistor in terms of mesh currents. That didn't really make sense. Well, no, that did make sense. What is the
R1
Yeah, I'm gonna. Yeah. Yep. All right. V2 is the voltage across that inductor. Yep. And V4. It is that voltage across that resistor 4. Oh, yeah. I'm sorry. Across R5. And yes, R5 times what? Yes. All right. I'm going to separate things into dependent and independent voltages. Yeah. All right. So I'm literally just manipulating this thing now to separate it. All right. So we will have GM over SC3 times V2, like you said, is SL2 IM1 minus V4, which is R5 IM2. Y'all agree? Cool. All right. Now, then we need to have that negative mu times V1, which is just R IM1. And then, excuse me. And then we have the same thing, but negative as the top. All right. I'll give you a second to write that down. Any questions so far? Making sense so far? This is natural frequencies we're doing. Cool. All right. I'm going to move on. So I'm just going to manipulate this and to turn it into a matrix times a vector. Yep. All right. So I'm also just going to factor this out. Just make it easy for everything. So we have GM. Those S's are going to cancel out. So it becomes GM L2 over C3. Yep. Excuse me. And we have GM R5 over SC3. And then in here, we have the negative mu R1 minus that GM L2 over C3. And then here, we just have the positive. I'm going to move this over just a little bit. And we have a positive, because that negative is going to factor in. GM R5 over SC3. Let's see if I agree with myself. Y'all agree with me?
I would have done it out and then simplified it.
I don't know what you mean by that.
I wrote everything out and then see.
Okay. Okay. Oh, as in like factor everything out? Okay. I can do that real quick. You want me to do that? Or do you just agree with what I got?
That's right.
Does it look decent so far?
Yeah, I think it is.
I was just saying, sit if you want.
Oh, my brain's fried. I just took my phone.
I understand that. Okay. And that is being all multiplied by IM1, IM2. Okay. So now, subtract this from the other side, right? So I'm just going to write from what I have earlier because it's a lot. Bear in mind, this is one of the longer problems in terms of what I have to give you all in terms of review. And Russell doesn't, no, he does, never mind. But I feel like he doesn't give this intensive name and name on the finals, or maybe the tests, I should say, but I could be very wrong on that. All right, now I'm subtracting this matrix from this matrix, right? So doing that, I then have an R1 plus SL2 plus 1 over SC3 minus a GML2 over C3. And then right here, negative 1 over SC3 plus GM R5 over SC3. That's my top thing. Then bottom, I got a negative 1 SC3 plus GM L2 over C3 plus mu R1. And then right here, I'll have 1 over SC3 plus SL4 plus R5 minus GM R5 over SC3. I think I made a mistake earlier. This is a negative. This is supposed to be a negative here because of that negative right there. I did make that mistake. My bad. I guess that would have been helpful to factor it out. But my bad. Does everybody see what I made that mistake here? I forgot to include this negative right there. Does everybody see that? Okay. Cool. All right. Oh, and that is all being multiplied by IM1, IM2, which equals just E, G of S. All right. If anyone wants to take a photo again of this problem, here's this. It's a little different from what I actually have written. I'm basically doing a network response question, moving it a little bit further, and doing natural frequencies. That is what I'm doing. So,
Convert it to a voltage source.
Yeah.
That's going to be in series with that capacitor.
yeah, sorry. Yeah. It's there in spirit.
It's
You
there
know
in
what I mean?
spirit.
Yeah, you know what I mean. Okay, so, okay, now we are here. Okay, so I am going to use what it said, and have the transimpedance, or admittance, I'm sorry, transimpedance function. So we need to find IM2 over EG. That's what we need to use, okay? So I'm going to write that up. All right, so actually, I'm just going to go ahead and plug these numbers in. It's relatively simple to do that. So therefore, this matrix, when you put in the numbers, which you can do in your own time, but I will just say, this is what I got, matches the solutions, we're good. I literally just plugged it into the calculator, and it gave me literally these functions. So 4.7 times 10 to the negative 6th S plus 10 over 10 S. And then I have 10 over 10 S right there. And then I have 940 minus 10 over 10 S. And then I have 10 to the negative 5S minus 10 to the 10 over S plus 200. Same thing. IM1, IM2 equals, yes. EG of S, that's G equals that. Yeah, I agree. So, like I said earlier, I'm going to use that transimpedance function that it says, which was y of t equals Im2 over Eg of s. How do we find Im of 2? Using a matrix. Cramer's rule. Someone tell me what Im2 is?
Bracket -1, bracket square 1 plus 2
I agree.
delta 1, 2 divided by delta times E6.
Yep. And so if I were to plug the Im of 2 into the transimpedance equation, those EGs will cancel out. Would you all agree?
Yeah.
Sweet. Cool. So that means a transimpedance function, I keep saying impedance, transadmittance function, I'm sorry, is negative. Y'all see why it's negative, correct? Okay. Delta 1, 2 over delta. I'm going to write that a little better. Do y'all agree with my statement? Okay. Yes. Yes.
Is that 940 or 440?
940.
And that's 10 to the negative 5.
10 to the negative 5, yes. 10 to the negative 5s. Yes. I will let y'all catch up for just a sec. Everything's making sense so far? This is kind of looking familiar? Looking familiar? Sweet. Cool. Cool. Do y'all know this is Russell's last semester? Yeah. Cool.
I should have gone to class, man.
I agree. But, yeah. So, yeah. Okay, moving on. So, can someone tell me what negative delta 1, 2 is?
Negative 940 minus 10.
I agree with the negative 940. I don't agree with the negative 10 over 10.
Oh, it's plus.
Yep. All right. So, delta. Can anybody tell me what that is? Give me just the brackets, or not the brackets, the parentheses stuff so I can explain it. All right, never mind. It is top left minus bottom right minus top right times bottom left. We agree? Sweet. All right. Then I have 4.7 times 10 to the negative 6th s plus 10 to the 10th s times 10 to the negative 10 to the negative 5s minus 10 to the 10 over s plus 200, all minused by 10 to the 10 over s, and then 940 minus 10 to the 10 over s. Make sense? Sweet. All right. You can do whatever you want here. I just literally plugged in the calculator. It gave me a form for delta. It's pretty easy. So delta equals, it's 47 times 10 to the negative 12 times s cubed plus 20 times 10 to the 6th s squared plus 1.128 times 10 to the 15th times s minus 157.446 times 10 to the 21st. And that is all over s. So now we got to take negative delta 1, 2, over delta. And that gives us our transadmittance function. So I'm going to go ahead and do that. Negative 940 plus 10 over 10 to the s over, I'm going to rewrite that, 10 to the 10th over s. And then you got that 47 times 10 to the negative 12, blah, 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 s cubed plus 20 times 10 to the 6th s squared plus 1.128 times 10 to the 15th s minus 157.446 times 10 to the 21st. Bracket all over s. Plug the two things in. All right. when literally plugging this into the calculator. And I also hit Control Enter because it gave me like a weird form, and I was like, I don't like that. So then I hit Control Enter, and it gave me the form of KNDS, as in K, or y'all know the form. So this is the final form of this equation. Negative 20 times 10 to the 12th times S minus 10.638 times 10 to the 6th all over S cubed plus 20 times 10 to the 6th S squared plus 1.28 times 10 to the 15th S minus 157.446 times 10 to the 21st. I'm writing it like 400 times. Yeah, I will give you all a second, and then we will move on. Everything makes sense so far? Process makes sense? Is this kind of similar to what y'all do in your processes? Yes, no, maybe so. Cool. Relatively easy to follow the process. Cool. So, as we alluded to earlier, I got one, and technically for this problem, this is the final solution. This is the final solution. But since I'm trying to kind of make this into a natural frequency problem, what do we do next? We alluded to this earlier. Poles and zeros. Okay. And we said this earlier as well. He's going to say, give us your short circuit and open circuit natural. Okay. Short circuit and open circuit natural frequencies, right? This is transadmittance. Now, alluded to earlier, what is in the numerator? What is in the denominator in terms of the short and open circuit natural frequencies?
No, the opposite.
I agree.
For transadmittance?
Admittance.
Yeah.
Admittance is
Short.
open on top, short on bottom. Does everybody remember why? I love explaining this. I don't know why. It's kind of fun. Yay, nay. Should I explain it real quick?
Yeah.
But cool. Okay. So I'm going to start with impedance. You got Z. Technically, when you break it down, you got V over I. Okay. When you have a 0 in the numerator, that means your function is what? No, I'm sorry. Mathematically, if you have zeros in the numerator, it's 0. It goes to 0. So if your voltage is 0, if your numerator is 0, that means if your numerator is 0, your overall, number is going to be 0, right? And what is 0 voltage?
A wire.
Which a wire is in terms of short or open circuits. Bingo. Short circuit. Therefore, impedance, short circuits in the numerator. Denominator. When you have a pole, it's a 0 in your denominator, meaning it's infinity. Okay? Also, when your current is 0, as in your current is in the denominator, therefore your current will be 0. What is that? Is it an open or short circuit if current is 0? Open. Boom. Flip it for why?
No, because it's like either the resistance is infinity or it's 0, which is pretty much like a short.
Exactly.
Pretty nice.
And then for minutes, literally flip it. That's how I've remembered it. Makes sense in my head because, open and short circuits. But okay, as we said, for admittance, though, it is flipped. So open will be on top, short will be on bottom. So therefore, our, I'm going to just say open circuit, omega n is what? Open circuit omega n. Okay, what's the 0 in the numerator? What would make that?
Oh, okay.
10.6.
So it equals 0 divided by 20.
Yep.
That's unbounded. Because it's positive.
Yes, because it is in the right half of the plane, it is unstable, meaning unbounded. Yes, that's a good way to put that. Yes, I forgot to say that. Yeah, okay, cool. Yes. Unbounded because it's in the right half plane. You have a positive number of the open of the imaginary and real axis, so you're on the positive side of that, meaning your system is unstable. It's unbounded, like you said. Okay. Does that make sense? Literally, you got the freaking axis thing. If you literally have anything over here, your entire function is unstable. That's literally that simple. All right. Now, short circuit, a little more complicated. you take this. Everybody got a TI Inspire?
Yep.
Okay. Does everybody know how to find the complex polyroots? Okay. You just do that. And then you'll get this. Okay. Negative 31.044 times 10 to the 6th. It's technically 2 poles. I'm just combining it into one because it's the positive and negative of the imaginary. 52.698 times 10 to the 6th. And then one more pole. 42.088 times 10 to the 6th. Okay. Yeah. Okay. Is it in this condition? Is it unbounded, stable, or whatever? All that stuff.
Is that like another pole? There's 3.
Yeah. So it's S cubed,
Okay.
meaning there's going to be 3 poles. So we literally have one pole that is positive. Therefore, that system is also unstable. That's simple. Okay. Any questions for this problem? Makes sense. I feel like natural frequencies is one of the easier things to understand because it's just name and name, and it does. It's a lot of work, but I feel like the process is relatively straightforward. Would y'all agree, or would y'all say something different?
No.
No? Oh, you do agree. Cool. All right. Sweet. All right. Let's move on to the second question. This is going to deal with rise back passivity. He's got one document that mentions it, period. It's like on one page of one document. 2 port properties. It's the only time it's there. And there's like 3 or 4 equations. I use one here. And there's also criteria, as hints in saying the rise back passivity criteria. That would make it whatever. I'll read the problem. By the way, this is the last problem on y'all's problem set 3. I didn't think anybody would re-look at it, so therefore I just did it. And it's also the only one that we got. So, all right, I'm gonna read the problem out. All right, 2-port open circuit impedance parameters, ZOC, of a linear passive network N at a low frequency are given below in matrix format. The trans resistance parameter Rm in ohms has been added to N as a variable to transform N into an active 2-port. Calculate the range of Rm over all possible values in this parameter, as in going from negative infinity to infinity, such that N is either passive or active. And you got to use, well, you can use a few things. The rise back passivity criteria, Mason's U function, or rise back's U prime function to help this calculation. I'm going to spoil it. I just used the first one. So for rise back passivity, you need 3 things to happen. Okay. I'm just going to define something real quick. K is just a uniform variable. You can substitute this for impedance or admittance, depending on what he gives you. So therefore, I'm just going to say that. Right? And I'm pretty sure in that document, I'm going to try to pull that up real quick. It says, I think it says it defines it in terms of Ks, but I could be wrong there. Like I said, I'm going to pull it up real quick. And this, I believe, is in materials, not 9, it's 8. You are correct. Literally, it's called 2-port prop. Yeah, in his document, it's defined as K, R, F, I, and O, which I guess I will also define it here. Okay. So this is KI. This is KR, KF, KO. That look familiar? Okay, cool. So, okay. For this to be true, so for it to be considered, yeah, what's up?
Yeah.
KF. Yes. Technically, it would be a forward bias. I'm not going to say that because that forward unilateral. That would make the circuit forward unilateral. It's in the same document. Okay, but yeah. So for it to be considered passive, the real part of Ki has to be greater or equal to 0. Ki is, the top left, 5K. Would you say that's greater than 0? But, okay. There's 3 parts. Number 2 is the real part of Ko has to also be greater than or equal to 0. Oh, okay. Real part of Ki is greater than or equal to 0, which Ki is the top left, therefore 5K. I would say that's greater than 0. Next part, real part of Ko is also greater than or equal to 0. And that is, I would also say the same. Cool. This is the one where you got to actually do math. I know, it's crazy. So it is the real part of Ki times the real part of Ko minus the real part of Kf times the real part of Kr. No, not the determinant. It's just that element. Well, yes, that is the determinant. I'm sorry. Yes, I understood what you're saying. It took me a second. And it's got to be greater than or equal to the absolute value of Kf minus Kr squared all over 4. This is on page 3 of that 2-port properties document. Okay. So I'm going to now plug numbers in. What is the real part of Ki? What is the numerical value? Yep. I'm going to do that. Oh, yeah, I'm just going to do that. What is the real part of Ko? Yep, I agree. What is the real part of Kf? Yep. What is the real part of Kr? I agree. That's 20. That's the wrong number. 2K. And that's got to be greater than or equal to. What's Kf? Well, I'm just going to say it again, whatever. Plus R M minus 2K squared. All over 4. So when multiplying everything together, we'll have 15 minus 4K. It's not 4K, sorry. My bad. Let me rewrite that. That's really, really bad. Okay, 2K plus RM minus 2K. My bad, guys.
I understood that.
I appreciate it. All right, cool. Now multiplying things together. 5K times 3K gives me 15
Million?
mega, yeah.
Oh.
You know what? I'm going to do this instead. Times 10 to the 6th minus 4 times 10 to the 6th plus RM times 2 times 10 to the 3. The M was kind of confusing. My bad. Okay, so yeah, I got that. And then, these 2 K's cancel out, and you're just left with RM squared over 4. Would y'all agree? Cool. Doing more math. 9 times 10 to the 6th plus RM 2 times 10 to the 3rd is greater than or equal to RM squared to the 4th, or divided by 4. Cool. I want this to look like a polynomial. Can anybody tell me why? Yes. The reason I am saying that, I'm looking for values of Rm which would satisfy this inequality. Correct. Exactly. So, therefore, I'm going to subtract that RM over. Or, I'm sorry. I'm going to move these over. I'm going to move these over.
You move that RM.
Also, I made a mistake. This negative factors in. No one caught that, guys. Come on. Okay. There we go. So, I'm going to subtract these two over. We got that. So then we'll have RM squared over 4 plus 2 times 10 to the third RM minus 9 times 10 to the sixth, and that is all less than or equal to 0. So I want to find the values of K that are gonna satisfy this equation. And you can literally do the same thing in terms of finding the complex polyroots. You don't really need to find the complex roots. You can just find the regular roots because it's going to be the same. After doing that, you get two values to satisfy this equation. RM can either be 3.745 or 11.7, and that's K, 3.75K, 745K, and then also 11.745K. Now, it's set a range, okay? And this is an inequality. We have found two values for RM, but essentially, if you plug anything that is in between these two numbers, you're going to get it that it's less than or equal to 0. Would y'all agree with me? If I put in, let's say I put a value of 2K into RM. Let's say if I do that, okay? I'm literally just going to do this on the fly. So I have 2 times 10 to the third squared over 4 plus 2 times 10 to the third times 2 times 10 to the third minus 9 times 10 to the sixth. It's got to be less than or equal to 0. We're going to find out if that's true. Y'all can do this too if you want.
They go with thanks to IEEE unplug all the calculators for all the.
That's all with that.
That's definitely true.
I got a value of negative 4 times 10 to the sixth. It's less than or equal to 0. Would y'all agree with that statement? So therefore, anything between this should work in terms of keeping it passive. Anything greater or less than those numbers will make it active. So therefore, I want to make it look like a number line. We're back to 4th grade. That's okay. That's negative infinity. This is infinity. I'm going to have two numbers. Negative 11.745K, 3.745K, and then zeros, somewhere like right there. So therefore, this range is passive, and then everything else is active. If y'all go over the homework that Russell gave y'all, this will be almost the exact same process, except Russell uses quadratic formulas.
If you just put the RM value, will you get full credit?
I mean, you'd have to explain that if it's in that range, it's passive, and everything else
If
active.
I set it up as an inequality, would that be like? That makes
Yeah,
sense.
yeah. Because I mean, I'm just visualizing the inequality here on number, like basically number line. So, any questions for this one? Like I said, this is literally the only things I have on this problem or like on this material. This is like basically all I've seen. There are two other functions that he mentioned, which were the Mason's U function or the Reisbach's U prime function. You can try those.
Can you give us the conditions for it to be active?
If it feels anything that's passive is active.
Outside of that
You know,
range.
like, do you know how you said like to be passive and you you gave us those three formulas.
Correct.
Is there something like that for active?
If it fails,
If-
that's
if-
it.
if at least-
If it fails any of them, if it fails any of them, exactly.
At least one of them.
Yes,
And then at that point, what do we do?
you just say it's active.
Is it?
Is it? So, yeah. Okay,
If show that one of them is false, so.
give me 1 sec. There's gonna be the next problem.
And ask when the hell is this?
Back it up into that.
Can you make this bigger? Can you make this bigger?
Yeah, I got you.
I know you don't.
A water.
I think so every day.
You're Jewish? That coin's falling out your wallet?
This isn't recorded.
Hey, John, get that, man.
Joking.
We'll cut that out.
All right, so this, as it says, is a active filter problem. Kind of weird, we'll work through it. It's actually relatively easy in my opinion. And it's also, this entire process is in the Book 2, Chapter 3 document. And I can explain where everything is at. Okay, so I'm going to start it off. I'll read it. The following specifications for a Salin and Key active RC low-pass filter, SAB, are given as follows. Those values. Design a filter by calculating values for R1, R2, and RA. Draw the schematic for this filter and label all the component values. Show your work and blah, 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 blah. Okay. Does anybody have any idea how to start? Okay. We have poles. What are poles? In a mathematical sense, what is a pole? Of a numerator or denominator? Denominator. It is the roots of the denominator, okay? And in finding things, it is important to have, though, that denominator. What I'm trying to say is step one is find technically our denominator of this formula or of this problem. How would I do that? I got two poles.
What would be like relatively easy?
To do what?
Just do like S plus 4.4K plus, and then just do,
Multiply it.
yeah. by
Exactly.
plus.
Exactly. So essentially, I'm going to say this. Finding and exactly what he said. You say S plus 4.4K. Do y'all understand why it's plus and not minus still?
Yes.
Yes?
Yeah.
Okay. So essentially, this, were you being true or? Okay, cool. So this number here is going to set our denominator equal to 0. So therefore, we want to set the opposite number here. So if we were to place this number into S, we would get 0. So then we have to have the positive part. We have to have basically the real conjugate, or we just have to have the conjugate. That's the word for it. Sure. I'm not a math major. Can y'all tell? Okay. And then we're going to do this first one as minus J. Stop doing the K's. I'm just do 10 times 10 to the third. Minus J 12.4 times 10 to the third. And then same thing here, except flip the imaginary. Plus 4.4 times 10 to the third plus J 12.4 times 10 to the third. Okay, and we just multiply it out.
What is the find?
Denominator. That's a. Okay, I'm gonna redirect right there. You're welcome. You're welcome. You're welcome. Okay, so when what do you call it? When multiplying that out, the denominator becomes S squared plus 8.8 times 10 to the third S plus 173.12 times 10 to the sixth. Great. We found your denominator. Numerator, Doesn't really matter. I'll explain that here in a little bit. All right. I am going to pull up that book 2, chapter 3 document. So let me do that real quick. Downloads, book 2, chapter 3. Best freaking document he has. I'm kidding, kind of. Okay. So as it said, which I will explain here in a second, Salin & Key active low pass filter. That is important. That is telling you what type of filter it is and how it was basically made. So I'm going to scroll. Oh, I got Salin & Key. Okay. Oh, well, this is not what I wanted to do. Okay. We'll go there. Salin & Key. I'm going to keep going down. Salin & Key biquad filter. Salin & Key biquad filter. Salin & Key low pass filter. Does that sound about what we need?
Yes.
Yeah.
Sweet. Okay. We have a series of equations. Okay. Also, I said the numerator doesn't really matter. Can anybody, does anybody know why I say that?
We already have the variable right there.
You have all the variables in the denominator. Exactly. As in that s squared is, by itself. The omega p over q is that 8.8 times 10 to the third. And then omega p squared is 173 times 10, 0.12 times 10 to the third, or sixth, or whatever. And then we have a whole bunch of equations here. We have that k LBP equals mu a. We have that omega p equals 1 over square root of r1, r2, c3, c4. And we have that equation here. W over p equals 1 over r2, c3 plus 1 over r1, c3 plus 1 minus mu a over r2, c4. Okay? Can anybody kind of see where I'm going with this?
We have the values go around also.
Yeah, essentially. So, but y'all see how I got to that? It's pretty easy. I found the denominator. Like I said, the numerator doesn't really matter because we already have that function. Technically, our numerator would just be whatever was here. So we technically already have our numerator too. But yeah, so I'm just going to use these. So I'm going to use that. I'm going to write down that first formula. Omega p equals 1 over the square root of r1, r2, c3, c4. Okay. Trying to find r1 and r2, right? Cool. All right, I'm going to write down that second equation as well. Omega p qp equals 1 over r2 c3 plus 1 over r1 c3 plus 1 over mu a over r2 c4. And we are given values for c3, c4, klbp or klp and rb mu a. So does anybody have an idea of how we should do this next? Or does anybody have any idea of what to do next? We'll move forward a little bit. We got 2 equations, 2 unknowns.
Oh, set of equals to 2.
No. Well, you could do that. I didn't think to do that. What I thought to do was substitution.
Yeah.
So we have R2 and R1 and R2. We only have one R1, but we have 2 R2s. Do y'all want to substitute for R2 or R1? I want to do R1 because there's less formulas to do. So I'm essentially going to rewrite this formula in terms of R1, set it equal to R1, and then just substitute there. Does that make sense? You can kind of see where I'm going with that? Cool. By the way I saw Russell do this, didn't understand it one bit. This way, I understood it a bit. So essentially, I am going to do this. Blah, blah, blah. Essentially, I'm going to multiply this over, well, I'll just do that real quick. Omega p times the square root of R1, R2, C3, C4 equals 1. Y'all agree? Okay. Now I'm going to divide the WP over. Square root of R1, R2, C3, C4 equals 1 over omega p. Does that make sense? Yeah. Okay, I'm going to square both sides. R1, R2, C3, C4 equals 1 squared equals, what is 1 squared? Yep. Times omega p squared. Okay. So that means that R1 equals 1 over omega p squared R2 C3 C4. I'm going to give you all a sec. By the way, I think we're probably going to end this before 1. I only have 2 more problems after this, and I think it'll be fine. Okay, so what do we do next? I have a function for R1. What should I do next? I agree. So omega p over qp equals 1 over R2 C3 plus 1 over omega p squared R2 C3 C4 times C3 plus 1 minus mu A over R2 C4. All right, we'll do a little bit more math. Those cancels out. What is 1 over something? Exactly. So that means omega p equals 1 over R2 C3 plus omega p squared R2 C4. I canceled out those C3s. That makes sense, right? Okay. Plus 1 minus mu A over R2 C4. Now the only unknown we have in this problem is R2. Would you all agree? Okay. Well, we don't. Those are the only unknowns. Can someone tell me, though, the value of omega p over q looking at this equation? Say that again. Yep. Can anyone tell me the value of omega p squared from this equation? Yep. So just put those numbers in. So, and then, I'm sorry. C-solve in the calculator. Best friend. Therefore, C-solve 8.8 times 10 to the third equals 1 over R2 times 47 times 10 to the negative ninth. 47 is the value for C3. 47 times 10 to the negative ninth is the value for C3 and C4. Plus R2, that's an R5. I don't know why I wrote 5. Times 47 times 10 to the negative ninth times 173.12 times 10 to the sixth plus 1 over, what is the value of mu A? KLP. And that is from here. Literally just that. So I just wanted to remind you. 1 minus 4.5 over R2 times, I don't know why I put a comma, 47 times 10 to the negative ninth. And then for those who don't know how to C-solve, literally type in C-solve for this entire thing and then do this. Yes. And then literally put a comma, R. Literally how to do it. It's your best friend. It's amazing. It's amazing. When that happens, you will get a value. I got 2 values, but one of them was negative. You can't really, you could have a negative resistance, but not really. So go with the regular one. And that regular one, or regular means positive in my brain, 3.154 K ohms. We're a third of the way there. Does that kind of make sense? Make sense so far? All right. So I'm going to use this part of this equation and just divide those numbers. Does that make sense? To get R1. So therefore, R1 equals 1 over R2 C3 C4 omega p squared. Okay. So that means that R1, plugging all the values in, equals 3.154 times 10 to the third times, these are the same values, so I'm literally just going to square them. 47 times 10 to the negative ninth squared times 173.12 times 10 to the sixth. Yes, sixth. And that'll give you a value for R1 of 829.042 ohms. That's a 9. I'm going to redraw that. It's a 2. Okay, we're 2/3 of the way there. Does that make sense how I did that? Sweet. Okay, last part. Oh, wait. I'm gonna wait a second until everyone's done writing because I'm going to flip from place to place. All right. So last but not least, we need to find RA or RB. I'm sorry. We need to find RA. We were given RB. So this is an active filter. What does an active filter use at its core? Op amp. Okay. Op amp, you have, feedback resistors or whatever. So we're given RB, we have RA, and we have a gain parameter. Just there. That's what we got to do. Also in the same document. So, okay. So that means if we have equals 1 plus RA over RB, that means that RA over RB equals KLP minus 1. Y'all agree? Make sense? How I did that? Cool. So that means RA equals RB times KLP minus 1. So the value, so RA is 1 times 10 to the third, because that's the value of RB, times 4.5 minus 1. RA equals 3.5 K ohms. Yeah, makes sense?
Were you getting the KLP that
It's given as 4.5 volts per volt. And KLP also equals mu A.
Yeah, that's all.
Yeah. Any questions on this one? Kind of made sense. Now I kind of understand y'all got a very confusing question on your midterm for active filters. So now you'll understand that document has a crap ton more things than actually I've only covered in the 2 problems. So, I would review that document a little bit. Okay, maybe not. But I'm just saying review that document a little bit, like kind of just get used to where you can see some things, just so it helps you navigate in the test, because I assume that y'all had a little bit of a time crunch the last one and didn't realize that that one was actually in that document until later on in the test. Apparently, I was told it was in the document. If it wasn't, it wasn't, but whatever. So, all right. I got 2 more problems. We're moving on to 3-phase. Wow, 3-phase is really straightforward. Y'all have seen this problem. This is on your homework. Russell literally gives out the same 3-phase problems for the last 5 to 10 semesters. So this is the exact stuff that I like. Your problem set 5 is the same problem set 5 for me, and the semester before, and the semester before, and the semester before.
And then he'll come up with new questions, bro.
Yeah. Well, he's gonna switch up on y'all on the test, not on the midterm, or not on this thing. So, yeah.
On your test, when you give the 3-phase problem, you just change the numbers, change.
I'm gonna be very honest. I don't remember that test. I trauma dumped that test. Some essentially forgot it as soon as I did it. And that was also 3 semesters ago. So I'm gonna be very honest. I don't remember. And he does not publish the finals. Or if he does, I completely forgot to download it. Like an idiot. So, yeah. Okay. So I'm gonna go ahead and read this problem. Pretty straightforward problem. So I'm gonna go ahead and do it. Okay.
I'm confident for circuits. I'm gonna get a 37.
That's going to be the class average, so you're fine. So a 60 hertz 3-phase Y to delta transmission network is shown in figure 45. RMS values for the phase voltages, voltage sources, are given below in polar format. Those. Values for the delta connected load network at 60 hertz are given below. Those. Calculate the value for VAB, BC, and VCA expressed in polar format. Display these voltages on the complex plane with their magnitudes and phase oriented and orientation clearly labeled. Calculate the values for load currents RA, RB, IA, IB, IC expressed in rectangular phasor format. And calculate the values for phase currents IA2, IAB, IC3 expressed in rectangular phasor format. Okay. What do we do? How do we start this off?
First, choose the.
Well, I'm sorry. I agree with what you're about to say.
Figure out
We-
either 9 or delta configuration you choose.
Yes. So this is in our sources are in a Y format. That means when it's saying phase voltage, that's also saying the same thing as line to neutral voltage. I don't know if y'all have heard that term or if y'all have just heard is phase voltage the only thing y'all have heard? Phase voltage is the only thing I've heard. Okay. I'm not going to use the line to neutral stuff. Okay. Phase voltage. So how do, from getting to the phase voltage to phase voltage, can anybody tell me what is the conversion?
Face to face.
From going from phase voltages to phase. Can anybody tell? From getting here to here, how do we do that?
Oh, you just do BA minus CB.
I disagree. It's not as simple as saying minus and plus. There is a formula involved. It uses a magic number that's under a root. It's in 3 phase. What number do you think's in that root? Square root of 3. Literally, doing this is to get the phase to phase voltage, you multiply the phase voltage by square root 3. So if you were given phase to phase voltage, you needed to find the phase voltage, you divide it by square root 3. But it's not as simple as saying, oh, we only multiply it by square root 3. There's also a phase shift involved. I don't really remember the specifics of why, but I remember there's a phase shift involved. I know there's a phase shift involved. I will say this. I misspoke earlier. You can literally just subtract VABC, or you can just subtract the 2 phases. I'm sorry. I misspoke there. I'm just saying there's an easier way than actually having to just plug it in. Because literally from here, I just know based on this here that you just multiply VA times square root of 3. But you also got to count that phase shift. And when you do subtract the 2 phases, you'll have that phase shift involved. But it's literally just you add 30 degrees. And I believe it's, if you're here, you just subtract 30 degrees. I believe there, but don't quote me on the second one. Do not quote me on the second one. Okay, well, this is recorded, so I guess it's going to be recorded. So okay. Yeah, someone's saying my name? Okay, cool, fair enough. All right, so therefore, part A, I'm going to find VAB. Well, I'm going to take VA, multiply it by square root of 3, and use that phase shift, 30 degrees, which is 0 at the beginning, so therefore 30 degrees. Literally that simple. You can subtract A and B, and you'll literally get the same number. VBC, same thing. I said VBC. That's a 2. That's supposed to be a 3. VRMS. We have to add 30 degrees to this one. So negative 30 degrees plus 30 degrees equals what? Negative 90. I agree. That's supposed to be a 9. D. And then VCB, same thing. Yes. My bad. We got 120 plus 30 gives us. I agree. This is making sense? Yep. Okay. We have essentially transformed this y source into a delta source. What we've done. Does that make sense? Do you all understand why? Understand how? It's kind of, we literally just did this, and you see that YB makes it like a delta. So whatever. Yeah. Okay. So B part. Find the load voltages. Can anybody tell me how we find the load voltages? Correct. Why do we do that though? Or why is it that easy?
Because now the nodes are connected to the.
Correct. It's in the transformed element. The configurations are the same. So, all right. IA equals VAB divided by Z1. Oh, I'm sorry. VBC. Does everybody understand that?
Yeah.
Cool. All right. Equal. Does anybody not understand that? Or we good?
From the graph, right?
Yes. Yeah. If you see here, basically make a loop. What's the current in there? It's IA. What's the load in there? Z. Why is ZA in there? That doesn't make sense. Whatever. Yeah. VBC square 3 120 VRMS square root. I'm sorry, that's not supposed to be square root. Angle. Thank you. Man, it's getting that time. Okay. Negative 90 degrees over 10 plus J10. Gives us a negative 10. Oh my gosh. I'm assuming that's what you were asking. Am I correct, or was there something? Okay, cool. IA equals negative 10.3923 minus 10.3923 amps RMS. Yay, nay.
Just what about the J? Oh, yeah, the J.
That does exist. My bad. Okay, so IB. Okay, IB equals VAB divided by Z2, which equals the square root of 3 times 120 volts RMS. That's the phase voltage, or the phase difference of 30 degrees, over 20 plus J 30. And so IB equals 5.1674. I'm not going to go that many. I'm just going to go that, whatever. Minus J 2.555 amps RMS. It's looking correct? Looking familiar to y'all? Okay. And then finally, IC equals VCA over Z3, which is that. Square root 3 times 120 volts RMS with the angle of 150 degrees, all over 10 plus J 30. IC equals 1.317 plus J 6.439 amps RMS. Making sense? Looks right? Sweet. All right. Now we got to find the IA2, IB1, and IC3. Can anybody tell me what IA2 is in terms of load currents? Well, I'm sorry, I kind of spoiled it. How do we find IA2? IA2, IB1, IC3. How do we find that?
IB minus IC.
Okay, why do you say that? Is there a certain process you use to to get that formula. Okay, KCL is what I was looking for. Whatever, but yeah, okay. So you got IA2 going into this node, you got IB going out of the node, and you got IC going into the node. So technically, everything going in equals everything going out. So technically, it would be IB. Do I need to explain this or we get? Okay, cool. IB. I just did, but okay. IC. And then subtract over, and so IA2 equals IB minus IC. Even though he said at the beginning, I know I needed to explain it, so you know, whatever. So then, putting the values for IB and IC in that equation, IA2 is 3.849 plus J 3.884. And that would just be amps RMS. So I've explained it, how to find the IA2. So I'm just going to kind of just write it down for IB1. IB1 equals IA minus IB. So when plugging in the numbers, IB1 becomes negative 15.559 minus J 7.837 amps RMS. And then IC3 equals IC minus IA, which when you plug it in with the numbers, IC3 equals 11.709 plus J 16.832 amps RMS. That's it. Does that make sense? Three-phase, relatively straightforward. Cool. I assume y'all have not been taught this in the class. If anybody plans on taking Fundamentals of Power Systems with Ken Rangi, it's going to be a very large part of that class. So yeah. Okay. Moving on. Oh, never mind. I'll take a photo. I'll leave. Let's do. Okay. That's it. That's it. That's it. So. All right. Last question. One more. Oscillator questions. It's an oscillator question. Oscillators are relatively easy in my opinion. That's what I think. So yeah. All right. I'm going to read whatever I can see. The schematic of yet another component-scaled sinusoidal oscillator that uses a blank blank. I'm going to go with current-controlled current source is what it says. Shown in figure 1. You may assume the network is properly biased such that the CCCS is operating in its linear region. You are asked to do the following. Calculate the frequency of oscillation in hertz. Calculate the value of the current gain parameter beta in alpha then amps per amp that would cause a sustained oscillation. Okay. Oscillators. What's step 1?
This one,
Yeah.
I agree. Name. So, therefore, I'm going to set it up. What is connected to node 1? You're saying SC1Y.
because it said minutes.
Correct.
Yeah.
SC1 plus what? I'm going to say G2 first, but yes. 1 over SC3. What's being shared between the two nodes? And?
The conductor.
Conductor and conductor. They're being shared, so they're both negative. That is the right thing. Why did I say C3? It's supposed to be L3. No one else got that. Okay. Negative G2 minus 1 over SL3. Then same thing here. And then, is there anything else being connected to node 4 or node 2? Yep. What sources are being connected to node 1? Yep. So that means okay. What's being connected to node 2? Yep. All right. What is I1 of S?
In terms of.
Nodal voltages.
It's gonna be SC1, V1.
Yep.
Yes.
I agree. So therefore, I'm going to rework this matrix. Say this. It's technically 0, beta, SC1, VN1, but that's also equal to 0, 0, beta, SC1, 0, VN1, VN2. Do we agree? Do we disagree? Oh, well, I hope that means agreed. Okay. So then I'm going to subtract that matrix over. SC1 plus G2 plus 1 over SL3. Negative G2 minus 1 over SL3. Minus beta SC1. And then same thing here. Oh, this is supposed to be 0, 0. Yeah, I would agree. Wrong thingies. Okay. What shall we do next? Well, actually, I'm going to give you all a second. Let me slow down and let you all ready. My beat.
Plug in numbers.
You can do that.
Determinant. Determinant. Plug numbers.
Earlier, I did it with plug numbers. This way, I'm going to just do the determinant. But why do we do the determinant? We want to find out. I'm basically laying out the steps. We're going to then separate it from its real and imaginary parts after we set the S equal to J omega. Therefore, we can find the real and imaginary, separate them into their two parts, find the two things we're looking for. Okay.
I have the algebra for this one already solved out.
Bet. I'm definitely going to believe you. So delta equals SC1 plus G2 plus 1 over SL3, G2 plus 1 over SL3 plus G, this is supposed to be G4, not a G2, minus negative G2 minus 1 over SL3 times negative G2 minus 1 over SL3 minus beta SC1. Y'all agree? Do y'all want me to go step by step in terms of algebra, or do you want me to just give you the determinant and say y'all can figure it out? Cool. I'll do a little bit. Yeah. Okay. So this is my determinant after doing all the math. It's going to look ugly, but then I'll help you simplify it. So we got SC1 2 plus SC1 over SL3 plus SC1 G2 G4 plus G2 G4 minus G4 over SL3 minus beta SC1 G2 minus beta SC1 over SL3. What should we do next? We have some things that we don't like. What are those things we don't like? The fractions. I don't like those. We could simply do multiply S over S. We could do that, but I don't want to do that. I want to also cancel out just denominator totally. So what I do is I multiply everything else by S, the whole determinant or denominator, so I can just get that out of the way. So then that'll make our determinant. S squared C1 G2 L3 plus SC1 plus S squared C1 G2 L3 C4. I wrote something down
I
wrong.
don't think that. There was
I wrote something down
It
wrong.
should be a C1 G2, a C1 G4, a beta C1 G2.
Yeah, that S squared was wrong. This is an S squared C1 G4 L3. I'm sorry, I wrote that wrong. In this term here, I added a G4. I'm sorry, this is supposed to be G4 and not G2. That's my bad, I'm sorry. I multiplied this by a G2, but it was not supposed to be multiplied. That's my bad. Okay, there. Yes. Yes. Here we go. Then plus SL3 C2, not C2. G2 G4 plus G4 minus S squared beta C1 G2 L3 minus S beta C1.
Can you give that when you're done with it, Brian?
So then, what would y'all suggest we should do for the next step? I don't want to pay for it.
Separate out the S squared.
As in kind of combine like terms?
Yeah.
I agree. So, for the S squared stuff, I'm taking everything that's got an S squared. C1 G2 L3 plus C1 G4 L3 minus beta C1 G2 L3. Now everything with an S plus S C1 plus L3 G2 G4 minus beta C1, and then everything without an S or anything is just G4. So, yeah. Now what do we do next? Wow, I was doing that.
First, we plug in the values right now.
Okay. That is a way to do it. I'm not going to do that, but that's not what I'm going to. I was essentially saying yes.
S is equal to J.
Yes. So now we J omega it. What is S squared when you plug in J omega?
-1.
Omega squared.
Omega squared.
Negative omega squared. And it is negative omega squared because J squared is -1. We got C1, G2, L3. You could probably do some more factoring, but I didn't. C1, G2, L3 plus C1, G4, L3 minus beta C1, G2, L3 plus S. I'm sorry. Yup. J omega times C1 plus L3 G2 C4 minus beta C1 plus G4. All right. Now what should we do next?
Separate the real parts and the imaginary parts.
I agree.
And make each one equal to 0.
Yeah, this whole thing should be equal to 0. I didn't do that before. Correct. Everything should be equal to 0. So I agree with what you're saying. What do y'all want to take first? Do you want to take the real or imaginary part first? If you look at both of them, technically both has a beta in it. Technically both has an omega in it. But
Take the imaginary
why do you say that?
because it's easier to solve.
Why do you say it's easier to solve?
I can just tell.
Okay. So essentially, the you set this equal to 0, you divide out the omega from 0, still 0. So yes, it is technically the easier part. Let's take the imaginary. Imaginary part of the J omega determinant equals 0 equals omega C1 plus L3 G2 G4 minus beta C1. Like I said, divide both sides by omega, that's gone. So that means
C1 4L3.
plus. That really does look like a 4. I didn't mean for that to happen. Whatever. So then we have 0 equals C1 plus L3 G2 G4 minus beta C1. So I'm going to add beta to the other side. Beta C1 equals C1 plus L3 G2 G4. Now I'm going to divide out the C1. Beta equals C1 plus L3 G2 G4 all over C1. Does that make sense so far? Okay. But when you plug in the values, beta equals 3. 3 amps per amp. We're halfway there. Or, what is it, like 34%? Never mind. It's literally just half and half. Makes sense so far? Okay. All right. Now we'll take the real part.
Is that G2 or C2? L3.
G2. It's C1 plus L3 G2 G4. And then all over C1. Okay. Now the real part. So then we have negative omega squared times C1 G2 L3 plus C1 G4 L3 minus beta C1 G2 L3 plus G4 all equals 0. You know what? I'm going to back this up out. C1 L3 G2 plus G4 minus beta G2 plus G4 equals 0. Everybody see how I did that? Okay. I'm going to add over this term. So I got negative omega squared C1 L3 times G2 plus G4 minus beta G2 plus G4 equals, I'm sorry, nope. That equals G4. I'm sorry. Now I'm going to divide this part out. Oh, that negative also should not exist because I added it to the other side. Does that make sense? Does that make sense? That's okay, cool. So now I'm going to divide everything out. Squared equals G4 divided by C1 L3 times G2 plus C4 minus beta G2. Yep. And then we'll take the square root of everything. G4 over C1 L3 G2 plus G4 minus beta G2. Yeah. Yeah. It's an algebra class in disguise. It was the whole time. So I'm going to give you all the numbers. I would like someone. What? I would like someone to plug this into the calculator and tell me what you get. Omega square root of G4, which is 4 over C1, 2 times L3, 0.5, times 2 plus 4 minus 3 times 2. Right? 4, yep. Tell me what you get.
Okay, so 2, that's 1.
Put it in the calculator. Okay, I'm just gonna do it.
I feel like I was really cooking there, bro.
You were, but you're not gonna like the final answer. That's
2 over like root what 2.4 or 2.8.
calculator gives you undefined plus J undefined, and that's the actual answer.
Wait, okay, but how are you supposed to know that on the test though? That's like.
Great question.
Yeah.
This was a test question, so great question. So technically Russell puts it's, where the heck is the thing?
This was gonna happen. Something's gonna
He
happen.
says it's equal to infinity. And technically, I don't know if undefined plus j undefined is equal to infinity. Would y'all say it is?
It's leading approaching.
It's approaching infinity, so technically, yes, it's
We'll never
infinity.
reach it.
Yeah. He literally does this.
Yeah. That's the answer?
That's the answer.
Okay, so, okay.
And he's saying it is basically, it doesn't oscillate. It's like unbounded. It doesn't oscillate. So, it's a great question. Great point. But so, yeah. I mean, you just got to be very confident in your math.
Yeah.
Essentially it. Which is, fun on a 2.5 hour test. Any questions? Any questions? I really thought this was going to take longer than this, but okay. Yeah, so for any other material, like I said, I did a review a year ago that has almost the exact same topics. Pablo did a review last semester. He covers a couple op-amp problems, and I think that's the only stuff that he covered that wasn't on y'all's items to review. Yeah. So, yeah, any questions on anything else?
Do you have a recommended strategy for band-aid?
No.
Try your best.
Try your best. That's the best. That's the best advice I got. Russell's Russell. Can't predict anything now.
The industry is that he curves, but he doesn't tell people that he curves.
Cannot confirm nor deny. What else? It's his last test. I don't know. It's kind of crazy. This is my last review. Russell's literal last test that he's ever going to give. So,
It's gonna be 10 questions.
all right. Well, I'm going to go ahead and end the recording. But yeah, I'm going to go ahead and end that recording.
This is a better time.
This is the easiest test. This is the easiest test I've ever made.